Welcome to session 2 of chapter Gravitation. In this session, we're going to learn about satellites. What are satellites? Satellites are heavenly bodies revolving around the planets. We can call them as heavenly body, or we also call them a celestial body which are revolving around the planets. So these celestial bodies or heavenly bodies, we are calling them as satellites. And these satellites are of two types. One is natural, which we are calling it as heavenly body or celestial body, and the other one is man-made or artificial satellites. Man-made satellites are those satellites which man makes on the earth and launches it up into the space to revolve around the planet. So these are two different types of satellites. Example of natural satellite is a moon, the best example of natural satellite of Earth. Moon is a natural satellite of the Earth made by God. So apart from moon, Jupiter has 14 such natural satellites. Saturn has 12 natural satellites. What about the man-made or artificial satellites? There are many artificial satellites launched by man into the space. The first ever satellite which was launched into the space was Sputnik 1, which was launched by Russia in the year 1957. India launched its first ever satellite, artificial satellite, in 1975, and the name of the artificial satellite was Aryabhatta. Now these satellites are revolving around the planet. They are governed, or the motion of the satellites, they are governed by certain set of laws which are showing how these satellites move around the planet. These laws are called as Kepler's laws of planetary motion. Kepler's laws were formulated by a scientist called as Johannes Kepler. He formulated the laws of planetary motion. There were three main laws. The first law states that all planets revolve around the sun in elliptical orbits, keeping the sun as one of the focus. That is, if suppose this is the sun, the planets revolve around the sun in an elliptical orbit, keeping the sun as one of the foci. So this is how the planets revolve around the sun. The second law states the area swept out by radius vector from the sun to a planet in equal times are equal. They are also called as law of areas, or we can say that the rate of change of area with respect to time is constant. So for example, this is how the planets are moving around the sun. This is sun. So if the planet is here at a particular time, it covers equal areas in equal intervals of time. Suppose it covers the area dA in a time dt, then dA by dt is constant. This also follows the law of conservation of angular momentum. The law of conservation of angular momentum. It also follows this law. And also, what is the significance of this law is that this law states that the planet, when it is revolving around the sun, moves rapidly, that is very fast, when it is near the sun. And as it goes far away from the sun, the speed of the planet goes on decreasing. When it is far from the sun, it moves very slowly, and when it is near to the sun, it moves very fast. This is the significance of Kepler's second law. Right? Now, let's move on to the third law and the final law of Kepler. Kepler's third law states that the square of the period of revolution of any planet about the Sun is proportional to the cube of the semi-major axis. Now what is the semi-major axis? Now the distance here, this distance is the semi-major axis. Okay, so this distance, we are saying that the time period, the square of the time period of the revolution of the planet, this is directly proportional to the cube of this semi-major axis. So we are saying that t square is directly proportional to a cube. So these are Kepler's 3 laws of planetary motion. Now moving on to how these satellites move around the planet. So let's see how the satellite is revolving in a circular orbit. So when suppose I throw this object above, what happens? The cap comes down. Why does the cap come down? The cap comes down because of the gravitational pull of the Earth. Now the same cap, if I throw with a greater velocity, again it comes down. But if I go on increasing the velocity in such a way that if I project this vertically upward, this cap will never return back to the Earth. Then that velocity, we are calling it as escape velocity. So this cap is trying to escape from the gravitational pull of the Earth and never return back to the Earth. So therefore, we define escape velocity as the minimum velocity of projection of body for which it will escape the gravitational pull of the Earth. Now when we have to launch a satellite, we have to launch a satellite in such a way that it does not fall back down or return back to the Earth. It has to escape the gravitational pull of the Earth and start revolving around the Earth or around the planet. So therefore, that minimum velocity which we require is called as the escape velocity. Let's find out what is the value of that escape velocity. Now suppose, consider a mass m lying on the surface of the Earth at a distance of r. So, the force of attraction due to the gravitational pull, it is given by minus gm into m upon r square. So, this is what we had learned in our previous session. That is, the gravitational force is directly proportional to the product of the masses and square of the distance between them. The negative sign implies that although the body is trying to go away from the gravitational pull, but the Earth is trying to attract it in the opposite direction. So therefore, we have this negative sign. Now suppose this body is trying to move away from the Earth through a distance dr, then the work done, a small amount of work is done. This work done, this is equal to F into dr, which is equal to minus gmm upon r square into dr. So now if I integrate this, I will get the total work done. I will get the total work done. So what is the total work done? Integration of dw is w, and here since I don't know what is dr, I just take it as the limits to be from 0 to infinity. G, m and n are constants, so they come out. So I have minus gm into m integration of 1 by r square into dr. Now what is integration? Integration of x to the power n is x to the power n plus 1 upon n plus 1. Integration of x to the power n dx is equals to x to the power n plus 1 upon n plus 1. We have 1 by r square into dr. So integration of r to the power minus 2 into dr. So where we have x, we have r, okay, and n we have minus 2. So we have this as r raised to minus 2 plus 1 upon minus 2 plus 1. So this I will get it as r raised to minus 1 divided by minus 1, or I will get this as minus 1 by r 0 to infinity. So what is this now? When I apply the limits, upper limit minus the lower limit, I will get this as minus plus gmn by r. So this is the total work done for the mass m to try to go away from the pull of the earth. So this work done, this is equal to the kinetic energy. So what is the kinetic energy? Half mv squared is equals to gmm upon r. Gmm upon r. So this mass and this mass gets cancelled. So we have v square is equals to 2gm by r, or v is equal to square root of 2gm by r. Now this v is nothing but the escape velocity. So we can denote it as VE. We can denote it as VE. So this VE is equal to square root of 2gm upon r. Now we can further simplify this. We know that g, acceleration due to gravity. In our first session we have discussed this. So acceleration due to gravity, this is equal to gm upon r square. So where I have gm, I will substitute g into r square in the above equation. So what will I get there? VE is equal to square root of 2 into g into r square upon r. So 1r gets cancelled. So we have square root of 2gr. So therefore, I can write escape velocity formula to be VE is equals to root 2gr. Small g is acceleration due to gravity. Now let us try to find out what is the value of this escape velocity. Now g, we know that it is equal to 9.8 meter per second square, and r is 6.4 into 10 raised to 6 meter. So if you substitute this here, we will get this as square root of 2 into 9.8 into 6.4 into 10 raised to 6, and if I calculate this, I will get this as 11.2 into 10 raised to 3 meter per second, or the escape velocity is equal to 11.2 kilometer per second. So this is the value of the escape velocity. Now it is important to know that this is a constant value because escape velocity does not depend on the mass of the body. It only depends on the acceleration due to gravity and the radius of the earth. So for any body of any mass to escape from the gravitational pull of the earth, it requires a minimum velocity of 11.2 km per second. So this is the formula for escape velocity and the value of escape velocity. This is just one step of learning how to put the satellite in the circular orbit. So now we have tried to pull or push or throw the satellite or launch the satellite into the space. Now we have to learn how to allow the satellite to keep moving around the planet without falling back to the earth. So for that, we need to learn about a different velocity called as the orbital velocity. The orbital velocity is the minimum velocity needed to put a satellite into a particular orbit around the earth. So when a satellite is put around the earth, it has to keep on revolving around the earth. So it requires a minimum velocity to keep on revolving around the earth. If this velocity is not enough, then the satellite will fall down to the earth. So therefore, there are two forces which are acting here. One is a gravitational force and the other is a centripetal force. Centripetal force is the force which acts towards the center. It acts towards the center. So therefore, now we have to equate the gravitational force with the centripetal force. So for the satellite to keep on revolving around the planet, the gravitational force has to be equal to the centripetal force. So what is the gravitational force? Gravitational force is F is equals to gmm upon r square. Again, we are considering a body of mass m which is at a distance of r from the earth. So this is the satellite which is of mass m and it is revolving around the earth. So it is not on the surface of the earth. It is far away from the earth. So the distance of the planet from the earth, center of the earth, is r. And this is the capital R is the radius of the earth. So we are saying that the gravitational force, this is equal to the centripetal force. The centripetal force is mv square by r. So we are saying that the gravitational force is equal to the centripetal force, right? So gmm upon r square is equal to mv square by r. Now this m and this m gets cancelled. So what we have here is gm, okay, is upon r square is equal to v square by r. Now what we'll do is, we know that this v, since it is moving in a circular orbit, we'll try to put the angular velocity here. This v is equals to omega into r. Omega is the angular velocity. So if we substitute this here, we will get this as omega square r square by r. So 1r and 1r gets cancelled. Now we say that gm by r square is equals to omega square r. Now let's take this omega on one side. So we get omega square is equal to gm upon r cube, or omega is equals to square root of gm upon r cube, right? Now what is omega in terms of time period? Omega is nothing but 2 pi f, or it is equal to 2 pi by t. 2 pi by t, time period. So this I can write it here like this as 2 pi by t is equal to square root of gm by r. Or I can say that t is equals to, what is t equals to? 2 pi divided by root of gm upon r cube. Or I can write this as 2 pi root of r cube by gm. Now again, gm is what? G is equals to gm upon r square, capital R, right? Because it is the acceleration due to gravity. Now gm is equals to gr square. So if I substitute it here, what will I get? T is equals to 2 pi root r cube upon gr square. Or I can write this as 2 pi r by g root of 2 pi r by r root of r by g. So r square comes out, so we are left with 1 r and 1 g. So we have time period, this is equal to 2 pi r by r square root of r by g. Now if this satellite is very close to the earth and we say that r is approximately equal to capital R, then what will happen to this? These two will get cancelled. So we have the time period is equals to 2 pi root of r by g. Now again, if I substitute the value of r and value of g, that is r is equals to 6.4 into 10 raised to 6 meter and g is equals to 9.8 meter per second square, then I will get the time period to be approximately 84 minutes. So this is depicting the time period of the satellite to rotate around or to revolve around the planet. So what is orbital velocity? What is the value of orbital velocity? So orbital velocity, I can say that V naught, this is equal to R omega, right? So what is this now? This is equal to, what is omega? Root Gm upon R cube. So R root Gm upon R cube. Or if I take this R cube outside, I will have R by R root Gm by R. So these two will get cancelled. So I have orbital velocity is equal to square root of Gm by R if small r is equal to capital R. That is, if the satellite is very close to the Earth. So this is our relation for orbital velocity. Now instead of Gm, if I have to write it in terms of G, then what will I get? So this is going to be V naught is equal to square root of gr square upon r, since Gm is equal to gr square. So this I will get it as square root of g into r. So I can say V naught is equal to root of Gm by r, or it is equal to root of g into r. Now what will happen if I try to calculate the value of this? So again, if I substitute the value of g, that is 9.8 meter per second square, r is 6.4 into 10 raised to 6 meter. Okay. So if I calculate this, I will get around 7.92 kilometer per second, or I can say approximately V naught is equals to 8 kilometer per second. So this is the value of orbital velocity, that is the orbital velocity of the satellite to revolve around the Earth should be 8 kilometer per second. Please remember this, it is not per hour, it is per second. So it has to travel in such a speed that it travels 8 kilometer in 1 second. So if it does not travel in this speed, then it tends to fall down due to the gravitational pull of the Earth. So today we learned about what is escape velocity, what is orbital velocity, what are the satellites, what are the different types of satellites, and also we learned about the Kepler's laws of planetary motion. So let's move on and study more about satellites, how they feel in space, the weightlessness, etc. in a next session. Thank you.